All right, so let's talk about the cerebral hemispheres a little bit more. So when we talk about hemispheres, instead of looking at the lobes, frontal, parietal, occipital, and temporal, now we're looking at the different sides of the brain, right? So the cerebral hemispheres, we have a left side of the brain and a right side of the brain. In general, our dominant hemisphere is contralateral, or the opposite side of our writing hand. So for those people who are right-handed, your dominant hemisphere is your left hemisphere. For those people who are left-handed, your dominant hemisphere is your right hemisphere. Now, I said to you that there are messages or fiber tracks going up from the body up to the brain and from the brain down to the body. Um, so there's this bidirectional change, but these fiber tracks, they can go and cross from one side of the brain to the other, or one side of the brain to the other side of the body. So the word contralateral, contra means opposite, lateral means side, right? So if someone who is contrarian or says on the contrary, they're saying the opposite. Lateral is the side, right? Ipsilateral is same side. Now let's take vision, for example. If you were to look at how the fibers leave the back of the eye, well, some stay on the same side and some cross over. So for vision, about 50% of the fibers cross from the left eye to the right side, and the other 50 stay on the same side. So we have a partial crossing to the other side. So that's contra and ipsilateral. We talked about dominant hemisphere. And we even have our non-dominant hemisphere, and that's important too, right? Because people are like, oh, you use your dominant side, but you don't use the non-dominant side. That's not true. We actually use both sides. And in fact, we have an understanding of different functions for the left and right hemisphere. Now, how do we get messages from one side of the brain to the other? Well, one of the major bands of fibers that cross is called the corpus callosum, right? So the left and right hemisphere communicate through that. Okay. Now, I mentioned that our dominant and non-dominant hemisphere, we have different things going on in the dominant hemisphere. Now, we're using a right-handed person as a frame of reference here. So in the dominant hemisphere, or the left hemisphere, you're going to see a lot of language, logic, and mathematical reasoning. In the non-dominant hemisphere, you're going to see things like music, intuition, and spatial processing. Now, it doesn't mean that this is an exhaustive list. These are just a few things. But for a right-handed person, this is the frame of reference. Okay. Now, what would happen if we were to cut the band of fibers that connect the left and right hemispheres, right? Well, that study was done, right? So Sperry and Gazzaniga, they cut the corpus callosum in cats, and what they found was that it played some role in seizures, right? But for human beings, Gazzaniga found that it didn't work for seizures, right? So something was happening with cats that wasn't working with human beings, but there were some other issues, right? Remember how I said our visual system, half of the fibers cross to the other side of the brain? Well, when see this bottle, I know if you just have the slides, you can't see it, but if I were to reach for a bottle, I need to be able to connect my visual understanding of space with my motor movement. And the problem is because half of those fibers went to the other side, I might reach for something and miss because there's not this integration between visual and motor functioning because of the cut fiber tracks. So that was an interesting finding about cutting the corpus callosum. Now, I did say that we have the anterior and posterior white commissures as other ways to communicate across the brain. So really, there are three fiber tracts responsible for speaking or sending impulses between the hemispheres. All right. Now, we also want to understand plasticity. Plasticity, plasticity in general is your brain's ability to adapt, modify itself, reorganize, however you want to say it. And what we know is that the flexibility of the brain is best at around birth to about 5 years old. So, in fact, there are cases of young kids requiring a hemispherectomy, right? So they're riding a tricycle, God forbid they get hit by a car and they land on one side of their head, causing significant trauma to one of the hemispheres. In principle, you could remove a full hemisphere and have um, mild deficits at birth to 5. But doing that same act as we get older, the deficits become more pronounced. So between 6 to 11, we refer to this as moderately plastic or flexible or adaptive. And by about 11, most of our neurons are pretty hardwired. Most of our pathways are pretty hardwired. So if there's damage, if a person has a stroke or has traumatic brain injury after 11, well, they're going to have far more deficits. Does that mean there's no uh, flexibility or adaptation in a brain after 11? Of course not. The brain does have some malleability, some flexibility even after 11, but it's fairly limited. So the last thing I'm going to do, and this will wrap it up for our series on neuroscience, is talk about different neuropsych disorders. So aphasia. Now, there are many different kinds of aphasias, but we talked about two. So as you may recall, an aphasia is an impairment in language. So Broca's aphasia would be when a person struggles to produce speech in a meaningful way. Wernicke's aphasia would be an inability to comprehend or understand language in a meaningful way. Now, these are not the only aphasias out there, but based on our lecture, these are the two that are relevant. Amnesia, we talked about retrograde and anterograde amnesia, right? So that's a loss of memory. Now, agnosia, uh, agnosia refers to an inability to recognize objects. Now, we recognize objects in different ways. The primary way we recognize objects is through vision. So we see something, we understand its shape, we understand its uh, um, just as three-dimensional properties, and we say, oh yeah, I know what that is. That is a bottle of water, right? So we use our visual system, but that isn't the only way we recognize objects. So I could have you blindfolded and put a series of objects in your hand, and you would, in general, be able to recognize what the object is based on touch. Another example might be if you woke up in the middle of the night and it's pitch dark out and you don't want to turn the lights on, you might use your hands to navigate where you're going. And when you touch the bed, you know it's the bed. When you touch the doorknob, you know it's a doorknob, because through the sense of touch, we also recognize what objects are. So, sense of touch is a second set of eyes, basically. So, when you cannot recognize what objects are, that is an agnosia, right? So, we talked about visual agnosia, we talked about tactile agnosia. There is a form of visual agnosia that happens when you cannot recognize faces, right? So that's referred to as prosopagnosia, right? And that's important to note, because when it comes to Alzheimer's, late stages, people sometimes struggle with faces and who people are. And lastly, apraxia. We talked about the cerebellum, we talked about the basal ganglia. If a person struggles with motor functioning, we call that an apraxia, right? So these are uh, neuropsych disorders that are linked to the brain and practical applications. So we'll stop there, and our next lecture will start developmental psychology.